All right, we're going to do this problem where it involves a little bit of archaeology and also carbon-14 dating and exponential functions. A wooden artifact from an ancient tomb contains 65% of the carbon-14 that is present in living trees. How long ago was the artifact made? The half-life of carbon-14 is 5,730 years. Well, we're going to use the formula for radioactive decay, which is A equals A0 e to the negative KT. K is a constant, but that constant can be expressed in terms of the half-life. K is equal to ln2 divided by H, and H is the half-life. So how carbon-14 is an isotope of carbon-12, and every 5,730 years, half of it will decay into something else. So you'll start off with some carbon-14, like say a 1 kilogram. In 5,730 years, half of that kilogram is turned into something else. Okay, we're going to go ahead and just fill some things out here. Now, we're going to let A0 equal 1, or you could say 100%. So we're going to start, it doesn't matter if it's 1 kilogram. We don't know actually how much started. It's actually probably a very small amount that was in this wood. But say it starts off as a 1 whole, and then we're going to say, well, in a certain amount of time to the present day, we have 0.65. So what's going on is that A0 is the initial amount of C14. That's the initial amount. See, if you look at this formula, A equals A0 e to the negative KT. If you put T is equal to 0, then A will equal A0 e to the 0, and e to the 0 is 1. So you get A is A0 when T is 0. And then A is the amount now. So the initial amount was a long time ago, we're going to find out, and A is the amount now. So A, in this formula, maybe I should point this out. This is the amount of C14. A0 is the initial amount. So it's the amount of C14 at time t. Okay, now t is what we're trying to find out. That's the question mark. So after how many years, I don't know, like thousands of years, hundreds of years, you went from one amount of 1 kilogram, 1 ounce, whatever, it's probably way smaller than that, to 0.65 of that amount. How long did that take? Now K is equal to ln2 divided by H, and H is equal to the half-life. So therefore, this is ln2 divided by 5730. So if I take my equation here, which is the amount of carbon-14 is equal to the initial amount, A0, times e to the negative KT, well, but K is, actually, let me just go ahead and write it like that. Negative KT. Let's start with that. Well, the A is 0.65. That's the amount we have after a certain amount of time. And then we start off with 1. And then e to the negative KT. Well, K, I'm saying is ln2 over H, which I found from another time in class. So I have 0.65 equals e to this stuff. Now, ln2 divided by 5,730 is a positive number. So we have e raised to a negative number times t. And so the graph is exponentially decaying. And our graph, I mean, it's very roughly, but it looks like this. Here's A0, and it decays. And the amount of time it takes for it to decay to just be half of this, if this is A0 divided by 2, is 5730. The thing is, my picture looks like it's actually touching 0. So this is y equals e to the, all right. Now, what I want to do is I want to find t. I have this equation. I have e all by itself, and so I'm ready to go on this. I'm going to apply ln to both sides. What I mean to say is I'm going to apply the natural log function. Why would I do that? Because the natural log function in the exponential base e, oh brother, base e cancel. ln e cancel out. Cancel, cancel. This is how you solve equations that have an unknown up here in the exponent. So you see where the unknown is? What I'm trying to get at the whole time. I want to find that t. It's sitting up there, but I apply ln to both sides, and no longer is there an exponent. Now we have ln, now we have t multiplied by a number. The number looks sort of scary, but it still is that. It's just it's ln multiplied by a number. The problem is my t looks a little bit like plus or something. Okay. Now what I'm going to do is I'm going to multiply both sides by the reciprocal of negative ln2 divided by 5730. So I don't know, I'll use this color. Negative 5730 ln2. I multiply both sides by that. And the deal is that we get cancellation. That's the deal. So, oh, there's the answer in the very bottom. So I'm going to get t equals negative 5730 ln 0.65 divided by ln2. Well, be careful. This looks like a negative number, but it isn't. And I'm going to try to explain really briefly why it isn't. If I draw the logarithm graph, I don't know. If I draw the logarithm graph, oh gosh. Let's move that down here. Let's move this over here. Okay. The logarithm graph roughly looks like what I'm going to draw right here. In here I have 1, 0. That's, maybe it's not that bad. I don't know. It's something like this. Probably wasn't that bad, actually. Okay. So the thing is this is 1, 0, and this is y equals ln x. And okay, now where is 0.65? So 0.65 on this graph is, someplace where I'm drawing. This is like 0.65 for x. For y, I don't know, but notice it's negative. Okay, you plug it in your calculator, though, and you get a positive number, because ln 6.5 is negative, and let me make this better. Oh my gosh. Oh, can you hear the music? If that's what you would call it. Okay, ln 6.65 is a negative number. I'm trying to show you. So anyway, this is the exact value that I've written down here. This is the exact value, and you need to write that down, I think, for a homework problem or a test problem. You need to write the exact value. But if you're in the mood and you have a calculator, then you can, but it has to be sort of a good calculator. You can say it's around 3,000 years. No, we'll do a little better, 3,561 years. So that's sort of interesting. If you happen to be an archaeologist and you found a piece of wood and you found out it was 3,561 years old, that'd be pretty awesome. So, okay. That is that. Goodbye, everyone. until next time, not going away forever, just for this end of this video. Okay, bye.